Imagine a world so cold that water freezes into solid ice. This is Titan, Saturn's largest moon. Titan is no ordinary moon. It's a frozen landscape where temperatures average around 17.9 degrees Celsius, 290 degrees Celsius. This might seem like an inhospitable place, but it's anything but. Titan's frozen environment hides a fascinating secret. Water and ammonia flow beneath its icy crust, creating a dynamic world where ice volcanoes shape the surface. These aren't like the fire-spewing volcanoes we know on Earth. Instead, they erupt with liquid water and ammonia. Imagine frozen lava flows cascading down the sides of these ice volcanoes. This interplay of fire and ice creates a mesmerizing, ever-changing terrain. So much more to explore on this enigmatic world. To understand what causes these unusual formations, scientists continue to study data from Cassini and other missions. But for now, the sight of ice volcanoes on Titan remains a mesmerizing testament to the mysteries hidden within our solar system. The Cassini space probe, the fourth to visit Titan, observed these unique formations up close. What it found was intriguing. Cryovolcanism is driven by the heat from Titan's interior, melting the ice and causing these eruptions. But why does Titan have such activity when it's so cold? The answer lies in its unique atmosphere and low gravity. With this heat and Titan's low gravity, only about 14% of Earth's, the conditions are just right for these cryovolcanic eruptions to occur. As we delve deeper, we'll uncover more about these fascinating geological processes that make Titan unlike any other place in our solar system. These volcanic eruptions are not the typical lava outpourings we see on Earth. Instead, they spew a combination of water and ammonia. The interaction between these elements, fire and ice sculpts, Titan's surface in unique ways. A continuous cycle of eruption and condensation carves intricate patterns into the icy terrain. These geological forces are not mere remnants of a bygone era, but active agents reshaping Titan's landscape even now. This interplay between fire and ice is what gives Titan its distinctive landscape, making it a unique world within our solar system. To truly understand Titan's unique landscape, we must delve into the Cassini-Huygens Mission, one of NASA's most ambitious space exploration endeavors. Launched on October 15, 1997, this mission was designed to study Saturn and its moons in detail. As the lava-like fluids flow across the icy terrain, they cool rapidly, forming intricate patterns that can stretch for miles. This dance of elements is not just a visual wonder. It also plays a crucial role in shaping Titan's topography and geological history. These findings have deepened our understanding of this enigmatic moon and the captivating interplay between fire and ice that defines it. As we continue to explore the cosmos, the dance of fire and ice on Titan serves as a reminder of the wonders that lie just beyond our reach. With future exploration missions on the horizon, we stand on the brink of unraveling more mysteries hidden within Titan's icy crust. The Dragonfly mission, scheduled to launch far in the future, aims to unveil the intricate processes behind Titan's geological activity. Equipped with advanced instruments and a rotorcraft capable of traversing long distances, Dragonfly will provide unparalleled insights into Titan's complex landscape. Meanwhile, the Enceladus Orbiter and Probe (EOP) mission, slated for a 2034 launch, will delve into the icy plumes of Titan's neighboring moon. Though not focused solely on Titan, the EOP mission will provide valuable context for understanding the geological dynamics within Saturn's icy moons. As these missions take flight, they promise to shed new light on the dance of fire and ice that defines Titan's landscape. Each discovery will not only expand our knowledge, but also inspire future generations to push the boundaries of human exploration. Imagine a world where every eruption of Titan's ice volcanoes is not just a spectacle, but also a window into the planetary system's past, where each plume of water and ammonia carries stories of billions of years of celestial evolution. As we peer deeper into the mysteries of Titan, we are reminded that our universe is a tapestry woven with threads of both ice and fire. And as future missions continue to unravel the secrets hidden within its icy crust, we stand poised on the threshold of even greater discoveries. For now, we watch and wait, anticipating the day when Titan's dance of fire and ice will be understood in all its glory. Methane, being lighter than water or ammonia, tends to float on top of the lakes. This stratification can create interesting chemical interactions within the lake bodies themselves. To understand this relationship fully, we look at how the composition of the lakes changes over time due to these eruptions and the subsequent rainfall. These volcanic events can alter the levels of different hydrocarbons within the lakes, creating a dynamic and ever-changing ecosystem. It's a reminder that even on such an alien world as Titan, there's a delicate balance of natural processes at work. And so, we continue to watch and learn from afar as the dance of fire and ice on Titan unfolds in all its complex beauty. For now, we appreciate the intricate interplay between Titan's ice volcanoes and its hydrocarbon lakes, a testament to the wonders of our solar system. As we deepen our understanding of this alien world, we're brought ever closer to unlocking the secrets of its enigmatic beauty. Enceladus, one of Saturn's smaller moons, is a prime example. Its south polar region features prominent tiger stripes, which are long, deep fissures that act as vents for geysers. The Cassini mission discovered these plumes in 2005, revealing that the heat generated by tidal forces and internal friction drives this cryovolcanic activity. Titan's active volcanoes spew these materials high into the atmosphere, creating a complex interplay between fire and ice. The Voyager 2 spacecraft captured images of these plumes during its flyby in 1989, giving us a glimpse into this distant world's geological dynamics. Though no active volcanoes had been detected yet, the Galileo mission observed signs of past cryovolcanic activity. Each of these moons presents a unique interplay of fire and ice, shaped by their specific conditions and internal heat sources. This dance is not just a scientific curiosity, but an essential part of the geological history of our solar system's icy worlds. As the water and ammonia rise into Titan's dense nitrogen-rich atmosphere, they begin to affect its composition. The introduction of these compounds changes the atmospheric pressure and creates unique weather patterns that are distinctly different from Earth's. Scientists believe that organic compounds, known as tholins, form in Titan's atmosphere due to the interaction between sunlight and the hydrocarbons released by these volcanic eruptions. These tholins contribute to the rich orange hue of Titan's skies and are a key component of its atmospheric conditions. For now, Titan continues to captivate scientists with its volcanic plains and the fascinating atmospheric conditions they shape. As we learn more about this icy world, we gain deeper insights into the diverse nature of our solar system's geological processes. Breathe in the vastness of space and marvel at how the smallest interactions can create such wondrous landscapes and atmospheres. As we delve deeper into the mysteries of Titan's ice volcanoes, we realize that these celestial phenomena are not merely distant curiosities, but integral parts of our solar system's story. The Cassini-Huygens Mission, which orbited Saturn from 2004 to 2017, provided crucial insights into Titan's eruptive history. During its close flybys, the spacecraft captured images of vast plains covered in volcanic debris and detected hydrocarbon gases associated with recent outbursts. Investigating these historical records allows us to understand how Titan's ice volcanoes have evolved over time, adapting to changes in the moon's internal heat and external influences such as seasonal variations. Imagine standing on one of Titan's volcanic plains, the crisp ice beneath your feet, a stark reminder of the powerful forces at play. Here, You are not just witnessing a distant curiosity, but a vital part of our solar system story, one that spans billions of years and continues to unfold. The constant cycle of volcanic activity on Titan offers a window into the Moon's geological history and its ongoing evolution. Each eruption, whether large or small, contributes to the ever-changing topography of this icy world. Methane rain, a signature aspect of Titan's climate, plays a crucial role in maintaining liquid reservoirs beneath the surface. These subsurface reservoirs are vital for the stability and eruption frequency of ice volcanoes on Titan. Observations from Cassini's radar have mapped methane-rich regions, revealing how rain affects the volatile landscape over time. By understanding this environmental context, we deepen our knowledge of Titan's geological dynamics and the forces that drive its ongoing evolution. As we gaze at Titan's frozen plains and towering ice volcanoes, we appreciate the intricate dance of elements that sculpt its ever-changing topography. Each eruption contributes to this evolving tapestry, offering a glimpse into the geological history and future of Titan's dynamic world. And as we continue our exploration, we find ourselves drawn deeper into the mysteries of this enigmatic moon, shaped by the interplay of fire and ice through time. The composition of these plumes includes a mix of water vapor, ammonia, and other hydrocarbons. Over time, these eruptions have had a significant impact on Titan's overall atmospheric chemistry. These interactions could potentially lead to changes in atmospheric composition over long periods, creating a dynamic and ever-evolving environment on this icy moon. Understanding these intricate interactions between geological processes and planetary atmosphere not only enhances our knowledge of Titan, but also deepens our appreciation for the complex interplay of fire and ice that shapes this distant world. The dance of elements on Titan continues to unfold, driven by the mysterious and powerful forces beneath its icy surface. This unique interplay is a testament to the incredible diversity and complexity found within our solar system. As we delve further into the mysteries of this enigmatic moon, we are reminded that every breath of air we take was once part of a distant star's fiery dance, a connection that binds us to the cosmic ballet played out on worlds like Titan. Perhaps one day, we will unravel more of these celestial secrets and come to understand how the elements have shaped not only our moon, but also worlds far beyond our own. Until then, we continue to marvel at the delicate balance of fire and ice that creates such a unique and captivating world as Titan. The Cassini-Huygens mission revealed intriguing evidence of tectonic faulting on Titan's surface. These images showed long, linear features indicative of geological fractures, suggesting that the moon is not entirely stable and static. Titan's low gravity, about 14% of Earth's, plays a significant role in these tectonic movements. This diminished gravitational pull allows for more pronounced tectonic activity, as the force required to initiate and sustain fractures is reduced. Imagine the ground shaking beneath your feet as a result of these tectonic shifts. This instability in Titan's surface can lead to the formation of new fractures and fault lines, creating pathways for the escape of internal heat. Providing us with a comprehensive view of the geological forces at play, this fascinating dance of elements further enriches our understanding of Titan's captivating landscape. The delicate balance of fire and ice creates a world unlike any other, continuing to capture our imagination as we explore the mysteries of this distant moon. The geological transformations are evident in the extensive lava flows and calderas that scar the frozen terrain. These signs of past volcanic activity serve as testament to the ongoing geological evolution on this distant moon. Scientists predict that future eruptions will continue to reshape Titan's landscape, carving new features into the icy surface. As we look towards the future, it is clear that these ice volcanoes will remain a driving force behind Titan's geological changes for millennia to come. This ongoing interplay of elements continues to shape a world unlike any other, offering endless opportunities for discovery and exploration. The dance of fire and ice on Titan is far from over. It is just beginning to reveal its secrets to us. As our understanding deepens, so too does our appreciation for the intricate beauty of this celestial ballet. To understand the mechanisms behind Titan's ice volcano eruptions, we delve into the unique dance of fire and ice on this enigmatic moon. At the heart of these eruptions lies a mixture of liquid water and ammonia. Pressure builds beneath the surface as these volatile substances rise through fractures in Titan's icy crust. Eventually, this pressure reaches a critical point, triggering an eruption that can fling material up to heights of hundreds of meters. This lower gravitational pull allows the eruptions to be more sustained and expansive than they would on a body with stronger gravity. As pressure releases and material is expelled, the icy surface of Titan undergoes dramatic transformations. This dynamic process reveals the beauty and complexity of Titan's icy ballet, driving its continual evolution. With each eruption, we deepen our understanding of the intricate mechanisms that sculpt this celestial body's enchanting surface. With each eruption, vast quantities of methane and other hydrocarbons are released into the atmosphere. These eruptions contribute to the formation of complex organic compounds that are essential components of Titan's atmosphere. The release of methane and other hydrocarbons into the atmosphere plays a critical role in atmospheric chemistry on Titan, driving reactions that can form more complex molecules. Long-term effects of these eruptions include the gradual enrichment of Titan's atmosphere with organic compounds that were not present when the moon first formed. The interplay between the eruptions and Titan's atmospheric conditions results in a dynamic system where new compounds are continuously being formed. Thus, the same forces that sculpt Titan's icy surface also shape its atmospheric composition, creating a world where fire and ice work together to create a unique celestial environment. This interplay of elements reveals the fascinating complexity that lies beneath Titan's frozen exterior. Ultimately, it is this dance between fire and ice that makes Titan such a captivating and enigmatic world. Scientists have observed that these eruptions can cause the temperature to rise by a few degrees Kelvin in the immediate vicinity of the volcanoes. These temporary temperature spikes can disrupt local weather patterns, leading to transient shifts in atmospheric conditions that ripple outward from the volcanic site. Over the long term, these repeated eruptions may contribute to broader climatic changes on Titan, as the accumulated effects of numerous volcanic events could alter the moon's atmospheric dynamics. Researchers have also identified potential feedback loops between volcanic activity and Titan's overall climate system, where the release of heat and materials from eruptions could influence larger weather cycles. For instance, a significant eruption might temporarily enhance cloud formation in the area, which in turn affects how sunlight is reflected or absorbed, impacting both local and regional temperatures. This complex interplay between fire and ice on Titan highlights the profound influence that these cryovolcanic events have on shaping the moon's climate over time, demonstrating the comprehensive impact of its ice volcanoes. These cryovolcanic events shape the moon's surface, leaving behind traces of liquid water and organic compounds that could be crucial for the emergence of extraterrestrial life. The presence of liquid water on Titan is particularly intriguing, as it's a key ingredient for life as we know it. Scientists are especially interested in the potential habitability of these cryovolcanic environments, where liquid water could interact with organic compounds to foster life's emergence. The Cassini-Huygens Mission has provided valuable insights into the composition and behavior of these cryovolcanic eruptions, fueling scientific interest in future exploration. Future missions to Titan could shed more light on the mechanisms at play and potentially uncover signs of past or present life forms that thrive in these extreme conditions. The search for extraterrestrial life is intimately linked to understanding these cryovolcanic events and their role in sustaining the conditions necessary for life's emergence. The possibility of finding life in these extreme environments is both thrilling and humbling, underscoring the profound impact that Titan's ice volcanoes have on our quest to understand the universe. Imagine a delicate balance where the slightest shift can cause a ripple effect. On Earth, tectonic plates move and grind against each other, forming mountains and causing earthquakes. Similarly, on Titan, these forces create stress and pressure points. Visualize the delicate balance that allows these geological wonders to exist and erupt in such a breathtaking manner. As we continue to explore this fascinating moon, each new discovery brings us closer to unraveling the mysteries of our cosmic neighborhood. For instance, consider the large impact crater known as SELC. Located near one of Titan's prominent ice volcanoes, this crater is a prime example of how external events can influence internal activity. The impact that created SELC released an enormous amount of pressure and heat, which in turn ignited the volcanic eruptions nearby. The interplay between these two forces, the internal heat driving volcanism and the external impacts releasing pressure, is what gives Titan its unique dance of fire and ice. This insight not only deepens our knowledge of this distant moon, but also provides a glimpse into the broader workings of our cosmic neighborhood. As we continue to unravel these mysteries, each new discovery brings us closer to understanding the intricate balance of forces that shape this icy world. And in doing so, we gain a deeper appreciation for the wonders hidden within our solar system. Beneath the frozen crust of Titan lies a world shaped by seismic activity. As the Cassini-Huygens Mission revealed, these hidden tremors carve intricate patterns across Titan's icy surface. Consider an event as subtle as a pebble falling on the icy surface. This triggers a cascade of seismic waves that travel through Titan's thick layers of ice. These waves propagate deep into the crust, sometimes reaching the moon's interior heat source. One such detection by Cassini-Huygens showed a weak tremor that managed to travel hundreds of kilometers. When an eruption occurs, it releases a burst of energy that can initiate new seismic waves. This interplay between seismic activity and volcanic eruptions forms a unique dance of elements on Titan. Imagine this dance occurring over eons, each tremor reshaping the surface, each eruption carving new paths for future seismic waves. Thus, the icy moon of Titan becomes a dynamic canvas, constantly shaped by the intricate interplay of seismic activity and cryovolcanism. Over time, these plumes can modify the chemical balance of Titan's atmosphere, creating potential feedback loops with weather patterns. The release of ammonia, in particular, can react with other components in Titan's atmosphere to form complex organic compounds known as tholins. These tholins are thought to play a significant role in shaping the moon's distinctive orange haze and potentially influencing its climate over extended periods. Moreover, the presence of these compounds can affect the absorption of sunlight on Titan's surface, altering the overall energy balance of the climate system. These atmospheric changes can lead to shifts in weather patterns, impacting surface temperature variations over long periods of time. For instance, increased tholin formation might result in cooler average temperatures due to enhanced sunlight absorption, while reduced levels could contribute to warmer conditions. Thus, the interplay between ice volcano eruptions and Titan's atmospheric chemistry drives a dynamic evolution in its climate over eons. Understanding these processes offers a glimpse into the complex and interconnected nature of planetary climates and their evolution over time. At the heart of this dynamic lies Titan's subsurface water reservoir, a vast expanse hidden below its icy crust. This reservoir is not merely a passive feature, it plays an active role in shaping the moon's landscape. The interaction between this subterranean water and the cold ammonia on Titan's surface creates a volatile mixture. As these elements combine, they produce powerful eruptions that spew plumes of icy material high into the air. As these eruptions occur, they deposit new layers of ice on the moon's surface, slowly altering its topography over time. Titan's ice volcanoes also impact its atmospheric chemistry. The eruptions release gases into Titan's dense nitrogen-rich atmosphere, creating a complex dance of fire and ice. This mixture of gas and ice particles can lead to the formation of organic compounds in Titan's atmosphere. Scientists believe that these organic molecules are the building blocks of life as we know it. For instance, the presence of hydrogen cyanide in Titan's atmosphere could indicate the potential for life-supporting processes to occur. The interplay between ice volcanism and Titan's unique atmosphere creates a dynamic system that is both fascinating and crucial to understanding the Moon's potential for harboring life. Illustrating how eruptions alter the chemical composition of Titan's air, these findings offer a glimpse into the intricate workings of our cosmic neighborhood. This atmospheric dance on Titan underscores the interconnectedness and complexity of life's building blocks across our solar system. As this icy volcanic mix spews out onto Titan's surface, it interacts with the Moon's atmosphere. This environment is rich in nitrogen and contains trace amounts of methane. These warmer conditions can affect the stability of methane in Titan's atmosphere. Methane is highly sensitive to temperature changes, and a localized increase in heat could lead to the release or redistribution of methane molecules. The methane cycle on Titan is complex and dynamic. Eruptions not only reshape the surface, but also influence the cycling of methane in the atmosphere, contributing to the Moon's unique climate patterns. Through continuous monitoring and advanced modeling, researchers can shed light on the interplay between Titan's icy volcanoes and its methane-rich atmosphere. These insights may even hold clues about the potential for life forms that thrive in such extreme conditions. The heat from Titan's interior drives a process called cryovolcanism, powering these unusual eruptions. But how do these volcanic activities contribute to the formation of Titan's distinctive hydrocarbon lakes? These lakes are composed of liquid hydrocarbons, primarily methane and ethane. The chemical composition of these lakes is a unique result of Titan's volcanic activity. Through this fascinating interplay between fire and ice, Titan's hydrocarbon lakes come into existence. So, the next time you look at images of Titan's hydrocarbon lakes, remember that they are a testament to the powerful forces shaping this remote world. Within this atmospheric mix lies a complex web of hydrocarbons that significantly influence Titan's ice volcanoes. These hydrocarbons are not merely present, they undergo a continuous cycle that drives the Moon's cryovolcanic activity. Imagine this: on Titan, hydrocarbons such as methane and ethane evaporate from the Moon's surface into its cold atmosphere. There, UV light from the sun breaks down these hydrocarbons, creating a haze that blankets Titan's sky. This complex interplay between surface evaporation and atmospheric breakdown is what fuels the cycle of fire and ice on Titan. When these hydrocarbons reach Titan's polar regions, they condense into liquid droplets that fall back to the surface as a form of rain. These liquid droplets accumulate in vast hydrocarbon lakes, creating beautiful yet unusual features on Titan's icy terrain. Amidst Titan's icy terrain, organic compounds play a pivotal role in shaping its unique landscape. These hydrocarbons are not just scattered about, they form complex layers beneath Titan's icy crust. Cryovolcanism, the eruption of ice volcanoes, drives these compounds to the surface, creating a dynamic interplay. As these compounds ascend through fissures and cracks, they undergo chemical reactions triggered by heat from Titan's interior. This process not only shapes the landscape, but also provides a natural laboratory for studying prebiotic chemistry. In these icy volcanoes, conditions mimic those believed to exist on early Earth, making Titan an invaluable window into the origins of life. Scientists speculate that these same organic compounds might have played a role in the emergence of life on our own planet. The potential for prebiotic chemistry in Titan's ice volcanoes highlights the fascinating possibilities hidden within this icy moon. Beneath Titan's icy crust lies a powerful force shaping its volcanic activity: gravity. The Moon's gravitational field influences the distribution of cryovolcanoes across its surface. Regions with stronger gravity tend to have denser and more frequent volcanic eruptions. Understanding this relationship is essential for predicting future ice volcanic activity on Titan. By studying how gravity and topography interact, we can gain valuable insights into the geological processes that continue to shape this fascinating world of fire and ice. As Cassini-Huygens continues to reveal more about Titan's landscape, we come closer to unlocking the secrets of this enigmatic moon. The core of Titan is a significant heat source for these volcanic processes, but what lies beneath the icy crust? Beneath the crust, scientists have detected an ocean of liquid water and ammonia, adding a layer of complexity to Titan's internal structure. Above this ocean lies another layer, a subsurface layer filled with ice particles that are thought to be constantly shifting and moving due to heat from Titan's interior. The heat transfer mechanisms within Titan drive this dance of fire and ice, causing the ice particles to melt and reform continuously. By understanding these subsurface structures and mechanisms, scientists can better predict and plan for future exploration of Titan's icy landscape. The stability and behavior of Titan's ice volcanoes are crucial for any mission aiming to explore this mysterious moon. Discoveries like these not only expand our knowledge of Titan, but also prepare us for the wonders that await in the outer reaches of our solar system. Titan is roughly 4.5 billion years old, nearly as ancient as the solar system itself. Its surface has undergone a series of geological events that have sculpted its ice-covered terrain. About 4 billion years ago, during the late heavy bombardment period, massive impacts shaped Titan's early surface. These collisions left craters that can still be seen today. Understanding this timeline helps us appreciate the vastness of geological time and the significance of these cryovolcanic events. They have not only shaped Titan's surface, but also offer insights into the moon's internal processes. As we continue to explore Titan and other celestial bodies, these geological timescales provide a framework for uncovering the history of our universe. They are like chapters in a cosmic book, each one revealing more about the wonders that await. And as we stand on the precipice of new discoveries, it's clear that Titan's ice volcanoes are not just geological phenomena, but also vital storytellers of our cosmic past. The plumes that result from these eruptions are not merely clouds of water vapor, but also contain other volatile compounds, including methane and nitrogen. These plumes paint a vivid picture of the ongoing dance between fire and ice on Titan's surface. The presence of methane, in particular, suggests that the eruptive material could also be enriched with organic compounds, hinting at potential prebiotic chemistry. Studies have indicated that these plumes rise high into the atmosphere, dispersing their content and contributing to the complex chemical composition of Titan's skies. As we gaze upon these eruptive events, we witness not just a geological process, but also a crucial chapter in the story of our cosmic neighborhood. And as these plumes continue to rise and fall, they leave behind a tale that is both ancient and ever-evolving, shaped by the ceaseless dance of fire and ice. This is more than just a story of geological activity. It's a testament to the relentless motion of our cosmic past. The force of these explosions can push material hundreds of kilometers away from the volcano's vent, shaping the terrain over time. Think of an ant colony, where tunnels and chambers are constantly being reshaped and expanded by the activity within. The resulting landforms can be quite stunning, with intricate patterns of icy formations that bear witness to the dynamic processes at work beneath them. It's like watching the slow, choreographed dance of a glacier as it carves a landscape over millennia, but on Titan, this dance is more abrupt and dramatic. Their energy comes from deep within the moon itself. Titan's internal heat is driven by tidal forces exerted by Saturn. These forces cause the moon to flex and stretch, creating thermal gradients within its core. This process, known as tidal heating, generates enough heat to power Titan's cryovolcanic activity. Radioactive decay within its rocky mantle also contributes to the moon's internal heating. Additionally, the friction caused by the movement of Titan's liquid interior adds to this thermal mix. These combined heat sources create a dynamic and unpredictable landscape on Titan's surface. Imagine the Earth with its hot spots and plate tectonics, but now envision a world of ice where these same forces can cause sudden eruptions. Understanding these internal heat sources is key to unraveling Titan's unique geological story. Titan's surface, already carved by the elements, undergoes a transformation every few years. This transformation is not driven by wind or rain, but by cryovolcanic eruption cycles. The periodicity of these eruptions is not random, it's influenced by the gravitational pull of Saturn. This constant flexing generates heat within Titan's interior, heating up the ice and causing it to behave like lava on Earth. The resulting eruptions are not just localized events, but part of a larger rhythm set by the celestial dance between Titan and Saturn. These cycles of fire and ice create a unique dance of elements that continually reshapes the moon's icy terrain. Titan's landscape is thus a testament to both the stability of these cycles and the dynamic power of cryovolcanism. Understanding this rhythm helps us appreciate the beauty and complexity of Titan's geological story. But on Titan, it's not until late August that the first volcanic activity begins. The low gravity of Titan, approximately 14% that of Earth's, allows these eruptions to behave differently. The dance between fire and ice on Titan is not merely a spectacle. It serves as a crucible for the creation of complex organic compounds. As these volcanic eruptions spew forth water and ammonia into Titan's atmosphere, they undergo chemical transformations driven by the moon's ultraviolet light. These transformations lead to the synthesis of hydrocarbons and other prebiotic chemicals, compounds that are essential building blocks for life as we know it. Consider how these volcanoes might serve as windows into Titan's internal workings, hinting at the existence of a vast subsurface ocean teeming with possibilities. Could this internal sea harbor life or hold clues to the origins of prebiotic chemicals essential for life? The intricate balance between Titan's icy surface and its internal ocean highlights an interconnected world where every element plays a vital role. This delicate dance might just be the key to unraveling some of the mysteries that lurk beneath Titan's frozen exterior. In this vast cosmic ballet, the icy crust and the potential for liquid water below are intricately linked, shaping not only Titan's present landscape, but perhaps even its future as a harbor for life. This insight into Titan's geological wonders underscores the importance of exploring these celestial bodies, unlocking secrets that could rewrite our understanding of the universe and its potential for life. These towering plumes interact with Titan's dense, nitrogen-rich atmosphere, creating complex wind patterns that circle around the volcanoes. The Cassini-Huygens Mission captured images showing how these wind patterns swirl and dance around the ice volcanoes, like a graceful ballet performed by nature itself. As these icy particles are dispersed, they contribute to the formation of hydrocarbon lakes and other features on Titan's surface. The constant eruptions and the subsequent redistribution of icy materials by atmospheric winds play a crucial role in shaping Titan's landscape. Understanding these dynamics not only helps us appreciate the beauty of Titan, but also opens new avenues for research into how life might have emerged in such extreme conditions. By studying the intricate dance between Titan's ice volcanoes and its atmospheric winds, we take a step closer to unraveling the mysteries of our cosmic neighborhood. These insights remind us that even in the coldest and most seemingly lifeless environments, there are intricate processes at work, sculpting the universe around us. As we continue to explore these celestial bodies, Each discovery brings us closer to understanding our place in the vast cosmos. The unique combination of these elements is a result of celestial impacts over millions of years. Evidence from spacecraft reveals numerous craters on Titan's surface, signatures of meteorite impacts. These impacts can heat the moon's interior, leading to increased volcanic activity. Imagine the immense power required to melt through ice and eject materials across vast distances, a testament to Titan's geological might. As we deepen our knowledge of the cosmos, we appreciate the grandeur and complexity of these distant worlds, and our place within them. Beneath Titan's frozen surface lies a world of intricate heat distribution that defies our expectations. These maps reveal that Titan's interior is surprisingly warm compared to its frigid exterior. This heat distribution is influenced by the low thermal conductivity of water ice. Water ice acts as an insulator, trapping heat within the interior and creating a stark contrast between Titan's warm core and its frozen crust. This unusual heat distribution drives the fascinating dance of fire and ice on Titan's surface. Volcanic activity on Titan is powered by this internal heat, erupting with water and ammonia in a process known as cryovolcanism. These plumes of volatiles rise into Titan's dense atmosphere, carrying with them a rich mix of organic compounds. The chemical reactions triggered by these eruptions create a dynamic environment on Titan's surface, where prebiotic chemistry may be at play. It's a fascinating world where the frozen meets the volatile, and the processes driving it could hold clues to the origins of life itself. The lava channels formed by these eruptions can be as wide as a football field and stretch for kilometers across the surface. From space, these channels appear as dark serpentine lines snaking across the bright ice surface, a testament to the dynamic processes at work. The ice volcanoes on Titan are not just a unique sight, they actively shape its environment through atmospheric interaction. These gases then float upwards, interacting with Titan's complex atmosphere. Titan's dense, nitrogen-rich atmosphere is more Earth-like than one might expect. These compounds are part of what gives Titan its distinctive reddish hue, a striking contrast to the pristine white surface of the moon. It's a testament to the dynamic interplay between fire and ice that shapes this extraordinary environment. The eruptions occur in periodic cycles, with observable patterns and recurring events that define Titan's geological rhythm. These cryovolcanic eruption patterns are a fascinating interplay of fire and ice, driven by the internal heat of Titan's core and the icy mantle surrounding it. As we delve deeper into these patterns, it becomes clear that Titan's cryovolcanic activity is not just a spectacle, but a predictable geological process that continues to sculpt its ever-changing landscape. These eruptions provide a glimpse into the fascinating interplay between fire and ice, showcasing the unique ways in which our solar system's bodies evolve and adapt over time. Perhaps the most intriguing aspect is how these periodic eruptions offer a window into the predictability and order that underlie even the most seemingly chaotic natural phenomena. As we continue to study Titan, it's clear that this icy moon holds many more secrets waiting to be uncovered, each offering deeper insights into the wonders of our cosmic neighborhood. This external influence highlights how the cosmic neighborhood is a complex web where even distant forces can shape our celestial bodies. The release of water vapor and ammonia into the air triggers a series of chemical reactions that shape atmospheric conditions. Though these patterns are different from those we see on Earth, they illustrate how fire and ice work together to shape Titan's climate. The continuous eruptions from Titan's volcanoes maintain a delicate balance within its atmosphere, demonstrating how these forces influence the broader climate system. This interplay of elements highlights the unique atmospheric dynamics that make Titan a fascinating celestial body to study. These plumes can reach heights of over 50 kilometers, equivalent to the height of a large mountain on Earth. As they rise, they expand, creating areas of low pressure beneath them. Moreover, these plumes carry significant momentum that affects global atmospheric circulation. As they disperse, they can lead to localized changes in wind patterns and weather systems across Titan's surface. Imagine standing at the base of one of these volcanoes. The ground might tremble slightly under your feet as a plume of ice and steam erupts into the sky. The heat from the volcano can melt parts of Titan's icy surface, creating a temporary pool of liquid methane that quickly evaporates into the air. This continuous cycle of volcanic activity and atmospheric changes contributes to Titan's unique geological processes, making it one of the most fascinating celestial bodies to study. As we continue to explore and understand Titan's ice volcanoes, we gain deeper insights into the complex interplay of fire and ice that shapes this remarkable moon. This dynamic process highlights the ever-evolving landscape and atmospheric conditions on Titan, inviting us to further investigate the mysteries of this icy world. Eruptions release large amounts of methane into Titan's dense atmosphere, temporarily altering its composition. As the methane plumes rise and dissipate, they form intricate patterns that can be observed from space. These events can lead to a decrease in atmospheric methane levels, which in turn affects the global temperature of Titan. However, the impact is not confined to localized areas. It propagates across Titan's atmosphere, causing widespread disruptions in the global weather patterns. Scientists are continually studying these events to better understand how Titan's volcanic activity interacts with its complex atmospheric dynamics. The far-reaching influence of ice volcanoes on Titan's environmental balance is a testament to the complex interplay between geological activity and atmospheric conditions on this icy moon. Understanding these disruptions allows us to piece together the intricate puzzle of Titan's ever-changing climate and surface features, shedding light on the mysterious workings of this distant world. These geological alterations are part of a vast, slow dance of elements on Titan, a moon where water and ammonia flow like lava over an icy terrain. Observing these long-term changes allows scientists to better understand the intricate puzzle of Titan's ever-evolving climate and surface features. These observations underscore the dynamic nature of Titan's geology and offer a glimpse into its ongoing transformation, even as we stand still in time. These eruptions are not merely local phenomena, they have far-reaching consequences on Titan's atmosphere. As the plumes rise, they interact with the dense, nitrogen-rich atmosphere that surrounds this giant moon. Each volcanic eruption injects a mixture of water and ammonia high into the sky, where these compounds undergo chemical transformations driven by Titan's extreme conditions. The volatile nature of these gases in such low temperatures causes complex reactions to occur rapidly, leading to the formation of a variety of organic compounds. These organic molecules then disperse across Titan's atmosphere, creating a dynamic and ever-evolving chemical composition that shapes the moon's climate and weather patterns. Scientists have observed changes in Titan's atmospheric pressure and temperature due to these volcanic activities. The presence of organic aerosols, likely derived from the plumes, influences how light is scattered and absorbed. In particular, these aerosols can affect the moon's albedo, the measure of its reflectivity, which in turn regulates how much solar energy is retained or reflected back into space. Moreover, the ammonia within these plumes can react with other atmospheric gases to form thin clouds high in Titan's sky, adding another layer of complexity to its weather systems. Understanding this interplay between Titan's ice volcanoes and its atmosphere is crucial for comprehending the broader climatic behavior of this enigmatic world. This interaction between fire and ice not only reveals the intricate workings of Titan's climate, but also highlights the extraordinary forces at play in our solar system. By appreciating these volcanic activities and their atmospheric impacts, we can better appreciate the beauty and complexity of worlds beyond our own. In the grand dance of elements on Titan, each eruption plays its part in shaping the atmosphere and revealing the wonders hidden within our universe's frozen frontiers. The heat distribution beneath Titan's surface is complex and influenced by multiple factors. Additionally, the decay of radioactive elements within Titan's interior contributes to the overall subsurface heat distribution. The combination of tidal heating and radiogenic heating creates a dynamic environment beneath Titan's icy crust, influencing its volcanic activity. This knowledge completes our picture of the fascinating interplay between fire and ice that defines Titan's landscape. With each eruption, we witness the grand ballet of elements at work on this distant world. These aren't just any organic compounds. They include complex hydrocarbons and nitrogen-rich molecules. They originate from the breakdown of simple gases, like methane and ammonia, under Titan's harsh conditions. The process begins with sunlight interacting with these gases in Titan's atmosphere, setting off a cascade of chemical reactions that eventually lead to the formation of these intricate organic molecules. Once formed, these organics rain down onto Titan's surface and become trapped in the subsurface, liquid reservoirs that feed its ice volcanoes. When an eruption occurs, these organics are propelled skyward, forming a striking contrast against the ice and water vapor spewing from the volcano. The presence of these organics affects the behavior of Titan's volcanism. They can alter the viscosity and flow properties of the erupting materials, influencing how the lava cools and solidifies. Their role in Titan's cryovolcanism is more than just a spectacle. It's a testament to the complex dance of chemistry and physics that sculpt this distant world. This insight helps us understand the complex interplay of chemistry that shapes Titan's icy landscape. By studying these cycles, scientists can better understand how Titan's icy landscape has evolved over millions of years and continues to do so today. The morphology of these icy structures varies significantly, with some resembling Earth's shield volcanoes, broad, gently sloping mounds formed by repeated eruptions of fluid-like materials. Others take the form of calderas, vast depressions created when the summit or side of a volcano collapses due to the emptying magma chamber. This interplay between water and ammonia leads to the creation of intricate patterns on Titan's icy surface. Lava channels, for example, can be as long as 13 miles, winding across the landscape in a serpentine dance. These ice volcanoes are not like their terrestrial counterparts. They do not spew molten rock, but rather icy slush and vapor. The Cassini spacecraft spent over a decade observing Titan's surface, mapping the frequency, duration, and distribution of these cryovolcanic eruptions. Data from Cassini revealed that ice volcanoes on Titan are not isolated incidents, but part of a complex geological dance. Scientists analyzed the temporal and spatial patterns of these eruptions, identifying intricate cycles and periodicities. These volcanic events occur with remarkable regularity, every few Titan years, which is roughly equivalent to a decade on Earth. The eruptions themselves last for several days before subsiding, leaving behind distinctive lava channels that can stretch for miles across the icy landscape. This continual cycle of fire and ice has sculpted Titan's frozen surface over millions of years, creating intricate patterns that can span vast distances. By studying the distribution of these volcanoes and their eruption frequencies, scientists have gained insights into the dynamic interplay between heat from Titan's interior and its frigid exterior. Understanding these cryovolcanic eruption patterns deepens our appreciation of how fire and ice continually reshape Titan's surface in a dance as old as the moon itself. One potential source is radioactive decay. As elements like uranium and thorium break down, they release heat, generating warmth within Titan's core. This process is similar to how the Earth's interior stays warm, contributing to our planet's own volcanic activity. This heat, combined with remnant heat from Titan's formation, creates a complex interplay that influences the frequency and intensity of cryovolcanic eruptions on its surface. By deciphering these mechanisms, we can appreciate the profound beauty and complexity hidden beneath Titan's icy exterior, where the dance of fire and ice eternally shapes this enigmatic world. The combination of extreme cold and the volcanic eruptions creates a unique dance of elements that carves out remarkable landforms on Titan's icy surface. Ammonia plays a crucial role in this process, as its presence helps to lower the freezing point of water, allowing the eruptions to occur more readily. These processes serve as a reminder that even in the extreme conditions of deep space, the fundamental laws of nature continue to shape and reshape the cosmos around us. These unusual volcanic activities spew out not lava, but liquids such as water and ammonia, releasing vast amounts of hydrocarbons and other gases into the atmosphere. The hydrocarbons released during these cryovolcanic eruptions react with sunlight to form complex organic compounds, contributing to Titan's characteristic haze layers. These organic compounds not only give Titan its distinct orange color, but also contribute to the Moon's rich atmospheric chemistry, creating a complex and dynamic environment. The constant interaction between these gases and compounds with sunlight and other atmospheric components creates an intricate dance of elements that continuously shapes Titan's environment. Scientists believe that these processes, driven by the internal heat of Titan and its volcanic activity, play a significant role in maintaining and shaping the Moon's unique atmospheric conditions. Understanding these cryovolcanic eruptions helps us appreciate the profound impact of geological phenomena on a planetary scale, even in extreme conditions. Tidal forces, the gravitational tug-of-war between Saturn and its moons, generate significant heat within Titan's core. Over billions of years, the slow breakdown of radioactive elements deep within Titan releases energy that helps maintain its core temperature. Understanding these subsurface heat sources provides a glimpse into the profound geological processes that sculpt Titan's unique environment. To fully grasp Titan's ice volcanism, we must delve into the enigmatic realm of radioactive heat. Radioactive decay generates significant warmth in Titan's interior, a process known as radiogenic heating. This internal heat plays a pivotal role in powering the Moon's cryovolcanism, the process driving its icy eruptions. As radioactive elements decay, they release energy that gradually heats Titan's core. Data from Huygens and Cassini highlighted the influence of radiogenic heat in melting Titan's icy mantle. Models based on this data suggest that radiogenic heating contributes significantly to the melting of Titan's icy interior. Think of it like a slow-burning furnace deep within Titan, steadily providing the energy needed for these geological marvels to erupt. The interplay between radiogenic heat and the icy mantle is a fascinating dance of elements that shapes Titan's landscape. Without this internal heat source, Titan might look entirely different, potentially frozen solid with no signs of the dramatic cryovolcanism we observe today. This intricate balance between fire and ice makes Titan a geological treasure unlike any other in our solar system. Understanding this dynamic helps us appreciate the profound processes that sculpt Titan's extraordinary environment. Scientists have observed that these eruptive plumes can alter the composition of Titan's atmosphere, affecting its temperature and pressure over time. What's fascinating is that these atmospheric changes can in turn influence the volcanic activity itself, a phenomenon known as atmospheric feedback loops. The Cassini-Huygens mission captured evidence of such interactions, showing how these atmospheric feedback loops can amplify the cycle of volcanic activity and atmospheric changes. Scientists studying data from the Cassini-Huygens mission discovered that these eruptions can release vast amounts of water and ammonia. This outpouring reshapes the Moon's icy surface over time, creating intricate patterns and features that would be unrecognizable without these periodic events. Observations also indicate that the eruptions are not constant. They exhibit cycles influenced by tidal forces from Saturn. These tides can amplify the internal heat distribution within Titan, triggering more frequent and intense eruptions during certain phases. Understanding these cycles is crucial for grasping how Titan's landscape evolves over geological timescales. The rhythm of these cryovolcanic eruptions weaves a narrative of natural forces at work, sculpting Titan's icy terrain into a living canvas. By deciphering the patterns and frequencies of these events, scientists can unravel the story of Titan's dynamic surface. Through these eruptions, we witness a dance of fire and ice that has been shaping Titan for eons. The Moon's unique combination of internal heat and external tidal forces creates a mesmerizing ballet of geological change. Then there are caldera volcanoes, which form from the collapse of a magma chamber after an eruption. On Titan, these appear as vast depressions in the icy landscape. The low gravity allows for the creation of these massive structures that would be impossible on Earth due to its stronger gravitational pull. Imagine standing on the edge of one of these colossal calderas, feeling the chill of Titan's frigid air against your skin. You look down into a vast depression carved by the relentless dance of fire and ice that has shaped this alien world over billions of years. The primary source of Titan's internal heat lies in the radioactive decay of its rocks. Just as on Earth, Titan's core contains elements like uranium and thorium that release heat energy over time. This process, known as cryovolcanism, involves the slow release of heat from the Moon's interior. Over millions of years, this residual heat gradually warms Titan's icy shell, driving the eruptions that sculpt its surface. Lastly, there is residual heat left over from Titan's formation billions of years ago. As a molten body cooled and solidified, it retains some of this primordial warmth deep within its core. By understanding these internal heat sources, we gain insight into how Titan's icy surface is constantly being redefined by the geological fire beneath it. As you stand on Titan's frigid surface, feeling the chill against your skin, you realize that the frozen world around you is a testament to this unseen interplay of fire and ice. The relentless dance of these elements continues, shaping Titan's landscape over billions of years, driven by the steady beat of its internal heat sources. And so, the icy world of Titan is not a frozen relic, but an active participant in the cosmic ballet of planets and moons. Instead, Titan's eruptions are governed by a different kind of heat, the subtle warmth from within its icy crust, driving what scientists call cryovolcanism. But the chemical composition of these cryovolcanic plumes is where things get truly fascinating. Ammonia, on the other hand, reacts with hydrocarbons in Titan's atmosphere to form a hazy reddish-orange smog that gives the Moon its characteristic color. This smog not only affects how light is scattered and absorbed, but also influences the complex chemistry of Titan's surface. But it's not just water and ammonia that make these plumes so intriguing. Methane and other organic compounds also play a significant role in Titan's cryovolcanic activity. Methane, for instance, can condense into liquid form at Titan's surface temperatures and collect in vast lakes. When these lakes are exposed to sunlight, they undergo complex photochemical reactions that produce a wide array of hydrocarbons. And as we watch this spectacle from afar, it's not just the eruptions that captivate our imagination. It's also the thought of what these plumes might tell us about the origins of life on other worlds. Perhaps, in the not-so-distant future, we'll have a better understanding of this icy moon and its fiery heartbeat, one that echoes through the cosmos as part of our shared story. These subsurface reservoirs of water play a crucial role in lubricating tectonic activity. Understanding this connection reveals how Titan's internal water reservoirs facilitate its ice volcanism, creating a unique dance of elements across the Moon's surface. By observing this dynamic interplay between fire and ice, we gain insight into the forces that shape not just Titan, but potentially other icy worlds in our cosmic neighborhood. This intricate ballet of natural phenomena underscores the complexity and beauty of our solar system, inviting us to explore further. As we continue to study these distant worlds, we may uncover more secrets about their formation and evolution, and perhaps even our own home planet's past. For now, Titan serves as a captivating reminder of the mysteries that still lie hidden beneath the cosmos, waiting to be discovered. The atmospheric chemistry on Titan is also influenced by these cryovolcanic eruption patterns. Volatile gases are released, shaping the Moon's complex atmosphere. Titan experiences significant tidal forces due to its orbit around Saturn. These forces contribute to the heating of Titan's interior, providing energy for cryovolcanic activity. Understanding this subsurface heat distribution helps us appreciate the complex and fascinating geological processes at work on Titan, where fire and ice coexist in a delicate balance. As these gases are ejected from the cryovolcanic vents, they interact with the molecules already present in Titan's atmosphere. This interaction is crucial to understanding how the composition of Titan's atmosphere is influenced by its ice volcanoes. Imagine tiny particles called tholins, which are created by the complex reactions between water, ammonia, and methane. These tholins play a significant role in shaping Titan's atmospheric composition, contributing to its unique color and possibly even influencing the formation of complex organic molecules that could be precursors to life as we know it. This dance between fire and ice on Titan's surface directly influences the composition of its atmosphere, creating a complex and dynamic environment that scientists are eager to study further. This intricate balance of elements offers insights into the complexities of planetary atmospheres and their evolution, reminding us that even on a frozen moon far from Earth, the dance of fire and ice is a fundamental part of our universe's vast tapestry. Though Titan's icy crust is only a few kilometers thick, the heat from its interior can lead to periodic volcanic activity. The Cassini-Huygens mission revealed that these eruptions spew out a mix of water and ammonia, creating temporary liquid reservoirs on Titan's surface. Over millennia, these periodic eruptions have carved out vast hydrocarbon lakes and reshaped the Moon's icy plains. Ultimately, it is this ceaseless cycle of eruptions that gives Titan its unique and ever-changing frozen identity.